Welcome to the last chapter. The last chapter. Yes, room for celebration. I'm going to take today, a little bit of time today, and then some time on Tuesday and Thursday of next week to get through this chapter. I'm basically just going to give you a brief introduction today. This will probably not be very long. And then next week we will finish up this chapter over 2 days and probably have an AP classroom or 1 or 2 little lab activities, data analysis, some things like that. After next week, we will have Pig Week. The pigs are here in their buckets, and you will have your groups assigned, and we'll do pig dissections. And then the month of May, we will meet 4 times before the AP exam, and those will be 4 separate exam review sessions that we will have. No test on Unit 8 as a reminder, but I still will check your Unit 8 notes. So we're getting near the end. So this chapter is about populations and detail about populations. There's a number of concepts related to how and why populations change and the makeup of different populations. And this is just the chapter's kind of intro diagram about a population being affected by births and immigration with an I, and deaths and emigration with an E, meaning individuals that actually leave the population to go to other regions. Pretty simple concept on the surface. There are some mathematical modeling that this chapter does that you'll read about. We will look briefly at that today and go into it in a little bit more detail next class. Yes?
Do you have a cough drop?
I do not, I'm sorry.
I do actually. I lost my voice, so I have a bunch. Yeah.
Okay, so a few terms that I kind of picked through from the beginning of this chapter that I want you to be familiar with. This concept of density, we use this term density with populations to indicate, essentially how many individuals are in a certain space, how tightly packed the population is. Of course, this has a lot to do with how much space is available to the population. So if you have a large space, you could have a pretty large population that's still not densely populated. The other term that I wanted to throw out at you is this idea of dispersion. Now, again, this is more just for a bit of literacy in this unit. I don't think that the AP exam would ask you directly just to define dispersion, but in the previous chapter we talked about dispersal, and I did want, since they sound a little bit familiar and mean kind of similar things, to delineate between the two. Last chapter I briefly mentioned dispersal, and that's essentially how organisms can spread out throughout the biome and how far they can get away from their point of birth. So we talked about the dispersal of that cactus, the saguaro cactus in the US Southwest, and its dispersal around the region and how far it could disperse. Dispersion is more of a look at how an individual population spaces out the individuals of that population. So it's not about how far away or how much around the world the population can spread. It's really about the distribution within that population. And they have these clumped, uniform, and random examples of how different organisms basically associate with one another in closer or more distant ways as just part of their day-to-day spacing in their population. So I would probably, if these terms came up on the exam, be familiar with the difference. All right. The chapter continues on with demographics and demography. These are terms you've possibly heard before. Basically, when you talk about demographics, you're talking about population-related statistics. And demography is the field that studies these statistics and learns how certain factors affect the health of a population, the longevity of a population, how fast or slow it's growing, etc. Survivorship curves are a demographic concept that I wanted to share with you because this starts to get into a little bit of Unit 7 and kind of evolutionary strategy. So survivorship curves give us an idea as to the point in life individuals of a certain species will typically die. And since we're all humans, I think we have this kind of, understanding or perspective that, people typically don't die in their youth or middle age, and then most people make it to an old age, and then, rates of death increase greatly in the elderly. But that's really just a human thing. That is one type of survivorship curve, and I'll show you the other two types on this graph. We are what it's called a type 1 survivorship curve, where we have very low death rates throughout much of our life. So you can see here, this is basically out of 1,000, how many survivors you would have over time. And on the x-axis, it's a percentage of the absolute maximum age you could be, which for humans is around 100. It's really like 120 if you want to get into like world records. But it's not until much later in life do we find human death rates spike on these curves. Here we have a ground squirrel. Ground squirrels live to be about 10 or 12 years old. So of course this is not years down here, this is percentage. And what you find with a ground squirrel is it doesn't matter if you're a young ground squirrel, a middle-aged ground squirrel, or a ground squirrel that's considered to be very old, the chances of dying are about the same throughout life. Which is, again, not the case with at least kind of modern humans, or really humans, no evidence that humans have ever had any other type of survivorship curve. And these ground squirrels have this other trajectory. And then you get some like these, clams or oysters, I'm not sure exactly what species this survivorship curve is for, but a lot of mollusks are like this, where the difficult time in life is actually when you're young and you haven't developed the protective shell. And so death rates in this third type of survivorship curve are very high amongst the young. But if you survive to a certain point, that's actually kind of the least likely time for you to die. And some of these mollusks, by the way, can live for centuries, like 400 or 500 years is how old we think some of them can live. So if you can make it to a certain point as a mollusk, in a lot of species, you have a long, long, long life ahead of you with a much lower risk of death. So these are kind of I don't know if I would call them evolutionary strategies, but at least products of the evolution and the form and function of these different animals. Okay, so in the second section, they start introducing some mathematical models to you. I am not too worried about the math right now. We'll look at it into a little more depth next week. But I honestly don't want to spend a whole lot of time on practicing these calculations because I don't know if there's even going to be anything from Unit 8 on the AP exam. But I'm going to skip ahead to just the last two slides here and talk to you about kind of this general equation here. And really what I want you to know is kind of what the variables mean in case they're referenced or in case there's a graphical representation of these functions on a question one day. Capital N refers to the overall population size. Okay? So I would at least want you at this point to kind of start thinking about what the variables are defined as.
You said what overall?
Overall population size, that's population total. That's what this uppercase N refers to. What's lowercase t? Time. So we're talking here about a function of the size of a population over time. So this is an equation that helps us determine and predict population size. R, and this is actually written right below it here, this lowercase r is growth rate. The lowercase r is the growth rate, which is essentially a measure of how many more offspring individuals will have in the future. And then here we see n again, which is the overall population size. So in this function, we have a change in population as time changes is a function of the rate of growth and the size of the population as well. So it matters how big your population is. You can have a pretty small growth rate, but if you have an enormous population, you can still add a very large number of new individuals to it from point A to point B in time. Now, the last slide I just wanted to show you real quick gives you an idea of what this exponential growth that all life is capable of looks like. In this case, the only variable we have a number for is the growth rate. So here we have a higher growth rate, here we have a lower growth rate. And this is not very complicated at this level, but with a higher growth rate, you have a shorter, what we call lag period in the curve before it hits an exponential spike. And with a lower growth rate, we have a longer lag period. So the higher the growth rate, the shorter this kind of flat line lag period is, and the sooner you will see exponential growth. Now, life is capable of exponential growth, but this is a very idealized and oversimplified look at what a population actually does in nature. Because what happens to any population that's experiencing exponential growth? In real life, what's going to happen? Yeah, you're going to hit a point where what happens? Run out of resources, run out of space. So in the next section, after introducing this basic idea of exponential growth, we're going to look at things like carrying capacity. We're going to do that next week and talk about what limits this exponential growth, how different populations deal with hitting that limit, and then move on from there. So make sure you do this reading. I just wanted to introduce you to the chapter, and we're going to stop there. You have quite a bit of time to work on the project, so please take advantage of that. And next week we will wrap it up and work on some AP Classroom and activities. See you next week.